Anyway, I just thought I'd throw that in. You know, one of my favorite sayings is that everything in math is connected with everything else in math. So here's the connection between complex numbers and calculus 3. All right. So how long did it take on it? 45 minutes? I only meant to take 25 minutes. But anyhow, that's all right. Are there any questions concerning recent outside events in this class? Like dominoes, stuff like that. I started to give you another supplement, and I didn't decide I wouldn't print it out because I had with enough other stuff to talk about. I sort of wish I printed it out. But anyhow, it will be on Blackboard, and I think I'd like to talk about what's on it, and then and that'll sort of finish out section 2 of whatever chapter we're in now, the integral chapter. And before I go to section 3, which is polar coordinates, I'm then going to go back and pick up more partial derivative stuff. So anyway, let me finish out section 2. And next supplement, problem 1 is going to be volumes. And I'm going to give you 4 volume problems to look at. Box, cylinder, cone, and sphere. And I think I call these A, B, C, and D. And what I want you to do is to come up with the standard formulas for each of these volumes. And so I'm going to work 3 of them in class, or at least get you started on 3 of them in class. And then the 4th one, the sphere, I'll want you to do it by the same techniques that I use for these others. Well, the box is no big deal. But anyway, so the main formula I'm going to be looking at is volume equals double integral over a base of function. This is for volume under a surface. So we have z equals f of xy. Z equals f of xy is the surface. And I have some region in here. And so just erect these walls on there. And that volume of that solid is given by that integral. Volume under a surface. And each one of these things I can sort of think of as volume under a surface. I might have to stretch it a little bit, but anyway. So the box. Well, pretty clearly, that's just a volume under the top surface. It's volume under this lid. I need to put that in the XYZ coordinate system. So I think it's best just put one corner at the origin, like so, and the edges that go to that corner will be along the 3 axes. And let's see, you want to call them A, B, and C, or you want to do length, width, and height, or what have you? You don't care? I like A, B, and C. So let's let the dimensions of this box be A, B, and C. As I like to say at the end, oh, it's as easy as A, B, C. Anyhow, So I need two things. I need to figure out what this bottom region is, and I need to figure out what the surface is. So let's see. So this surface up here, that's going to be z equals f of xy. What will my function be if I just want the top plane of that box? Like, here's a box right here.
Z equals some number.
Z equals some number. Which number? Multiple choice. A is A, B is B, and C is C.
Oh, C.
C, okay. C. So we have here Z equals C, and that's what my function is. Yep. And now,
I was testing you passed.
so now I got to take care of this region. So, okay, my region is what kind of figure? My base region. Rectangle, okay. And so let's see, I need to do an integral over a rectangle then. So let's see. There's really not any pressing reason to twist this around, but anyway, here it is. So the volume is now going to be a double integral of this function c, and I choose an order of integration. You want dx dy or dy dx? Dy dx. Marvelous. Okay. And I got my function in there, and now I just need some limits.
0. To B? No, to C. I'm guessing so.
A goes along which axis?
The X.
The x. And this is an x integral, so A. And y goes along, y goes along this axis, that's B, so, this is A 0 right here, and this is 0 B. So this one is B. And, could I factor this integral?
Yes.
Yes. First of all, the c is a constant, just factors out the whole thing. And then, let's see, all the limits are constant, and there's no insides anymore. So I've got 0 to A, dx, and 0 to B, dy. And when you integrate the differential, all you get is the length of the interval. So this is c times A minus 0 times B minus 0, or again, as easy as ABC. It's one thing to know that formula and to know about volume under a surface. It's another thing to actually, make everything match up and have this nice orderly progression from your picture to your answer. Cylinder. So this would be an obvious way to set up the cylinder. And let's see. Again, I don't like to use R for radius in Calculus 3, so I'm going to do what I always do and use A for radius. Radius A, and I equals H. And so let's see. I need a function here. I want z to equal f of xy. What'll that be?
x squared?
That would not be a coordinate, that would be an area.
What was your question?
But what is the function gonna be?
On,
3/4 pi r cubed.
oh, it's just gonna be,
Oh, it's
Again, you're telling me the answer back there.
Would it
it's gonna
be,
be like a circle.
would it be x squared plus y squared over a squared plus h?
No, it's gonna be.
Square root of a squared minus x squared?
No,
I want the function.
it's gonna be x squared over a squared plus y squared over b squared.
D equals c.
C equals C, but C is not in this story. H, okay, all right. It's another constant. The top thing is a plane, and it's not this kind of plane, it's flat, horizontal plane. So, same thing as over here. Now, let's talk about the base, the boundary here. So I've got a circle. My base is a circle. And the radius is A. Now tell me something about with squares in it.
X squared over a squared plus x squared over b squared.
What's B? B is A. So if you insist on doing it the hard way, then I'm going to take the B squared, I'm going to replace B with A, and then that's 1. So I think we were talking about the ellipse, right? So you were using the ellipse equation.
So can we just do x squared plus y squared equals?
That's what I do.
A squared?
You know, I could ask hard questions if I wanted to, but we'll just go with these easy questions and see how complicated you can make them. Yeah, I don't have the answer yet. All right, so volume equals the double integral. Oh, and again, what is, speaking of the answer, speaking of getting this finished, what is the answer?
Volume of the cylinder.
Volume of the cylinder.
Pi a squared h.
The value of this kind of problem, and I've been emphasizing this all semester, is that, you know, I'm not really proving much in this class. I never proved that this is actually a correct formula. I did give you some plausibility arguments in terms of volume by slicing. But it would be, if I'm going to rely on this, it would be nice to know it gives the right answers in the cases I already know the answers for. So I always believe in testing these things out. Everything new we do, I want to test them on the stuff we already know. So that's the point of this exercise. So anyway, integral over the base, f of xy, dA. And so this is just h. And I choose an order of integration. We did dy dx a while ago, so we'll do dx dy this time. And this is going to be what now? What are my limits on y?
From 0 to a.
From 0 to a.
Oh, no.
I mean,
from negative a to a.
Negative a to a. All right.
Same
Now,
thing.
I could use symmetry and go from 0 to a and just double it, or actually do fourfold symmetry if I wanted to. But anyway, negative a to a, and then what about x?
Negative a to a.
Then I'd be doing a square. So the limits were constant for the box, but the limits are not going to be constant for this thing.
Would it be negative root a squared minus y squared to root a squared plus y squared?
You got it. what did he do? He just took this equation, he said, I'm gonna look at this typical y coordinate between minus a and a. How about this one right here? So then I'm gonna traverse this with x. I wanna go from, see where it goes in, where does it come out? Both of the, where it goes in and where it comes out are on the same curve. I'm gonna solve this curve, this equation for x. And I'll use the square root method, so that's plus or minus the square root. And so where it goes in, that's the negative square root, where it comes out, that's positive square root. And after one step, let's see, h times x. From negative square root to positive square root, integrate negative a to a. Get rid of the ellipse. And then dy. And so when I put this in here, I'll have h times the square root of a squared minus y squared minus h times the negative square root of a squared minus y squared dy. And I'll leave it to you at this point. I'm now in calculus 2. You can either you might know the answer for this kind, or you might use trig substitution. But I'm going to say etc. And at least we'll have h as a factor in the answer, and I think we've done this kind already, so I'll leave that alone. Now, I want to work the cylinder again. I want to work the cylinder again in preparation for when I start working on the cone. Because this approach to the cone would not work very well at this stage in our Calculus 3 education. So, I'm going to start over with the cylinder. And I'm gonna cast myself back into the 19th century and early 19th century and Lincoln and rail splitting and all that stuff. Chop this, chop it again. So I've got these 4 pieces, and throw away 3 of them, or burn 3 of them, or whatever, and then knock the other one over. So I'm going to think about it like this. Do the same thing twice. Now I don't have a flat top anymore. But I do have a rectangular base. All right? This will be an easier setup, except for the function. I'll have to work harder for the function. So, I want z equals f of xy equals what? For that, I need to start thinking 3-dimensionally and thinking about the equation of a cylinder in 3 dimensions. Now, looking back at the original here, the circular base here was x squared plus y squared equals a squared. What if I graph that in 3 dimensions? What's the graph of x squared plus y squared equals a squared in 3 dimensions? It's a cylinder. So basically, here it is with z equals 0, and there's no z in the equation, so if z equals 1, it would still be the same x's and y's. If z is 2, the same x's and y's. So when you are missing a variable in an equation, then the graph of that thing in 3 dimensions would be the same as the graph in 2 dimensions, but you just move it parallel to the axis you're talking about. Well, so this quarter circle is part of a complete circle. What's the equation of that complete circle? which plane is this? So what's the equation of the circle?
X squared equals C squared equals A squared.
Yep. And now I want to solve that for z because I need a function of x and y. Well, so I'll get plus or minus the square root, but I'm only going to do the top part. So I'm going to get plus the square root of a squared minus x squared. And I'll get that volume, that's the quarter cylinder, I'll multiply by 4. So, volume equals integral of f of x, y, dA over the base. And I've got the square root of a 4 times. So this is the total volume here. So this will be a squared minus x squared. And we'll choose an order of integration.
dx dy.
Dx dy. All right. So, y limits.
Zero to h.
0 to h. Yeah, because again, the base let's see, on the x-axis, we're going 0 to a, because that's the radius. On the y-axis, we're going 0 to a. And so, that's the y limit, 0 to h. What's the x limits? 0 to a. Yeah. Because it's a rectangle. All constant limits, you got a rectangle. This integral factor. Can I factor this integral? Whenever I've got all constant limits, then it's a candidate for factor. So I can just say this right there. As far as y is concerned, that's just a constant. In fact, it is just a constant. I lost the 4. That's just a constant. And so I can bring that constant out of the y integral. And then what's left? I've got a very puny hollow integral right here. And this thing just gives me h. And again, I'll leave it to you to do the trig substitution and get done with that. Your answer should be pi squared over 4. And then when you multiply by 4, you'll have pi squared times h. So anyway, etc. But finish the details. But you'll notice I will have the minus here. This will be 2 times the square root of basically the same quadratic except with a different variable. And because it's minus a to a, I'll get twice as much as if I went 0 to a. Anyway, now I'm ready for the cone. Here's the cone. I'm going to locate that right there. The axis. But this one looks like a tougher problem. This is a more substantial, more respectable problem. And, so I need this top surface, and it's not as easy as it was earlier. And for this, I'm gonna have to take time out and talk about another section that we skipped. We skipped the section on what are called quadric surfaces. Quadric surface, well, that's a degree 2 surface in 3 dimensions. All right? And so I think I'll just take time out and do that for a while. And because the cone is a quadric surface. The equation of the cone is degree 2. I think I'll go into some of these other ones first. I'm going to start with, well, somebody trotted out the ellipse equation a while ago. I'm going to do you one better. So this is time out for quadrics. I needed to do this sometime this semester. So I had this written down a while ago. This is the equation of ellipse. How is that ellipse situated in the plane?
On the origin.
Around the origin, okay. And
On X, Y.
then on the X and Y axis. Okay, so I'm not doing this kind of ellipse, although it sort of looks like that. Anyway. So A and minus A, B and minus B. And this is X and Y. And if I were to put this in 3 dimensions, then what I would get for this equation is just a cylinder, not a circular cylinder, but what's called an elliptical cylinder. With this, Z doesn't matter in this equation. Well, what if I wanted to sort of go with this? Let's let Z get into the action also. This will not be an elliptical cylinder. Z does matter, but it's the same kind of idea. So, all right, my XY trace is an ellipse, but my XZ trace is also an ellipse, and my YZ trace is an ellipse. So basically, all the cross sections on this thing are going to be ellipses. And I cannot possibly draw this thing.
Like an X.
Even if I were trying harder. I'm not really trying very hard anyway. Anyway, watermelon. And anyway, name, this is called an ellipsoid.
AKA watermelon.
Yeah, aka watermelon, yes. All right. And if 2 of these denominators were equal, but not 3 of them, it would still be an ellipsoid, but there would be a little more symmetry involved. So if, for instance, A and B were equal, then the cross section here would be what? Circle. So what we would have, think of that as a circle. It would be like we revolved an ellipse around the z-axis. So that would be an ellipsoid of revolution. We could get its volume by the disk method or something. Anyway, so there's that. If A, B, and C are all equal, what do I have? Sphere. Okay. So there's not much else to say about that. At some point, we're going to be looking at the volume of the ellipsoid, but not tonight. So the next thing to do, what's another? what are all the possibilities for second-degree equations, second-degree graphs in 2 dimensions? We got ellipses, circles, what else?
Hyperbola.
Hyperbolas and parabolas, okay. Those are the conic sections. There are some other things that are known as degenerate second-degree equations. For instance, if I have x squared equals 1, and I do this in 2 dimensions, then x is plus or minus 1. Well, x equals plus 1 is that line, and x equals minus 1 is that line. And this is the graph, and these 2 lines are the graph of x squared equals 1. And that's not a conic section. I cannot get that by taking a cone and cutting it with a plane. But anyway, if you've got any curvature in a second-degree graph, then it's either one of the 4 that we listed. Circle, ellipse, hyperbola, right. Well, anyway, for hyperbolas, what do you get for the equation of a hyperbola? What do you do to this to get a hyperbola?
Just have a minus between the x squared.
So if we change the sign, then we've got a hyperbola. Well, what if we change the sign here? And I'm going to change the sign between y and z. So with all pluses, it's called an ellipsoid, but now what's it going to be called? A cone.
A circular hyperbola.
Hyperbola. Okay. And again, if A and B are different, it won't be circular, it'll be an elliptical hyperbola. But anyway, let's see. If I look at the traces, the XY trace is an ellipse. The XZ trace, well, let's do the YZ trace next. That's a hyperbola. And is hyperbola opening which way? Along Y or along Z? Along Y. Because there is no Z intercept here. I mean, if this is already out, and I put Y equal to 0, then minus equals positive. That's what it works. So it opens this way. And this one's another hyperbola. When we do this, it's just that it's not quite the same shape. But anyway, I'm not even going to try to draw the XC one in here. I'm just going to say, okay, all these cross sections, the horizontal cross sections are ellipses, the vertical cross sections are hyperbolas.